So we're writing it here. So tau 11, tau 12, tau 13. This three component of the stress is acting over this area. About this area, this three component of stress is acting. Tau 22, sorry, tau 21, tau 22, and tau 23. This three stresses is acting over this area. So area number 1, so area number 2, and the third one, tau 31, tau 32, tau 33. These all are acting. So in the box there is a 6 phase. So remaining the same thing is same amount of the stress is acting over the opposite direction in a opposite manner. That is the representation of the stress we are telling. Now here we are considering one tetrahedral element. Of fluid. So it's a tetrahedral element of the fluid. Oh, we are considering here the fluid is under motion or rest, it does not matter. We are considering a fluid is under motion. Why it is taken choose the tetrahedral fluid element? Because we consider here same way as a 1, 2. Because how many surfaces there? There are total surfaces, the 4 surfaces. Out of 4 surfaces, 3 surfaces are the special surface. Special one. That means one surface, if you draw a normal to one surface is along x-axis, along y-axis, along z-axis. And another is the one general surface. 3 special surface plus 1 general surface. That's why we are choosing the tetrahedral element of the fluid. Tetrahedral having a 4 surface, out of 4, 3 special surface and 1 general surface. What are the special surface? If you the naming of it A, B, C, and Z. So this AOB surface is the special surface. Because from the surface, if you draw from this surface, if you draw a normal line, it will be along x-axis. It's along x-axis, normal line from the surface. Another way, the surface AOC along z-axis. If you draw a normal line, and BOC along y-axis. These 3 surfaces are the special surface, and the surface of ABC is a general surface. Generalization of it. Now we'll see again the representation of it here. So this was x1, it's the y direction and z direction. The same naming we are doing it. A, B, C. So first we draw the force component which is acting over it. So above over the surface AOB, the stress component first we are drawing. So that is tau is along 1, because area from the area, if you draw a normal, it is along x-axis, that's why 1, and force direction is also 1. It is outer from the surface, so tau 1. Same way, if you draw here, that will gives you a tau 1. And you draw, that will gives you tau 1. So 3 forces, 3 stresses are there. 1 normal stress and 2 shear stress. Same way, in this surface, if you're talking about BOC in this, what would be the stress components? 1 stress is a normal stress downwards. It is a tau. From the area, if you draw a normal line, it is along the y-axis, so tau 2, and as well as there is similarly here tau 2, 3 along z-axis, and tau 2, 1. So you can be able to see from the area AOB area, the stress components are tau 1, 1, tau 1, 2. These are the stress components. Area BOC, tau 2, 1, tau 2, 2, tau. And the area AOC over this area, what is acting? Normal, tau 3. Area, from the area, if you draw normal, it's along the z-axis, so 3. And that is also is a normal line, so tau 3. That's what gives you tau 3, 2. And this one gives you tau 3. These are the stress component. We can first represent it. What are the stress component of an element is acting now? So tau 3, 1, tau 3, 2, tau 3. These all are the stress element we are talking about here. Now, if you consider here over the surface, the general surface, what is that? General surface is A, B, C. This is the general surface. From the general surface, if you draw one normal direction, one vector, unit vector, that is the eta. We are talking about the eta. Okay. Taking it as a eta. And this is the unit vector of the general surface. And the stress is acting here, that is the general stress. We can consider it as the tau I traction vector. From the general surface, the traction vector we are considering. What is eta? Now our consideration, what is eta? Eta is eta 1 into I plus eta 2 into j plus eta 3 into k. The vector quantity. So along x-axis, along y-axis, along z-axis. Now, the surface area, the magnitude of the surface area here, the surface area here is the S. What is the surface area? It's the S. S is the surface area of for now. In this consideration, I'm talking here to see the surface area. S is the surface. S we are considering the surface area of ABC. The area ABC having a surface area is the S, and the unit vector is the eta. So if you multiply this S eta in I direction, if you do the dot product, S eta, S is the magnitude, eta is the unit vector. So we can write it S eta. So here representation, I am just again I have to erase some part. It will some portion after erasing, I will tell you it is a better way. Otherwise, next page it will be some confusion on that. I hope this part you understand. For the several times I'm repeating, so it's not about a problem. So this vector area, what is the area vector here? Of the area vector of the ABC, we can write it S into eta, magnitude into vector. So this area into dot product of I, what will comes? It will comes SN1. What is the SN1? SN1 is nothing but this one, this area, ABC, ABO or AOB, area AOB. Because if this area we dot product, the projection area will get AOB, this part. Same way, if we do the dot product with the z-axis, we will get for that area A z-axis. So sorry, okay, B O C. The same way, from the general surface, if you dot product of the K component, the projected area will get in this way. Area AOC. This for this one, this. So all area dimension we are getting it. So what is the area of AOB? Area of AOB is S and 1. Area of BOC is S and 2. And area of AOC is equal to S. These are the areas we are considering. Now, if you do the force balance along x-axis, along y-axis, and along z-axis, or you are applying the Newton's law, anything. If we are considering the fluid is at motion, if you considering here the fluid is at motion, okay. So if you considering it as a fluid is at motion, just you think about it. Just Again, in writing, along x-axis, what are the forces acting here? What are the stresses? This is acting tau 1 over this area. What is the area? Tau 1 into S. Here, along x-axis, what is the forces acting? This force is nothing but, we are writing it, tau over this. If you draw it, so 2, 1, S. About this. What are the force? Tau, the stress into area. We are converting it into the force. Yes. This 3 force is acting in the negative x-axis. All forces are known as the surface force. The force is acting over the surface. Self-explanatory is surface force, and another type of force is known as the body. So surface force plus body force will gives you mass into acceleration, because it is the net force over the element. The net force over the element is surface force plus body force. That will be equal to the mass into acceleration from Newton's laws of motion. We are getting. Okay. So surface force plus body force. So how many surface force are there here? If you consider here surface forces, so along x-axis, we are considering only one along x-axis first. So one by one we'll do it. So along x-axis, the force is acting here minus n n1, because it is a negative x. So minus 2 1 s into minus 3 1 s. These 3 surface force in these 3 corresponding area, A, B, C, O. So area AOB, this force is acting. Area ABOC, this force is acting. Area AOC, this force is acting. What about the common area? What are the forces acting? We consider here the general surface ABC. That was the tau I n eta, tau I eta. Okay. So tau I eta along x-axis. What about the along x-axis? Along x-axis, so it can be written as the tau 1 eta. But it is the positive x side. It is the positive x side. Tau 1 eta into s. So this total surface force plus body force. Body force means, now body force we have to consider. So along x-axis, the body force is Bx. Bx is the body force per unit mass along x-axis. Similarly, By for body force per unit mass along y-axis, Bz for body force per unit mass along z-axis. What we are considering here only. So what is the force? So Bx into the mass of the fluid, mass of the element. What is the mass of the element? Density of the element, fluid, into the volume. What is the volume of this tetrahedral part? The volume is known in the tetrahedral part is SH. What is the mean of SH? It's the volume of this element, of tetrahedral element. What is S? S we know. S is already defined, the surface of the common area. What is H? From the origin, if you draw a normal over this ABC surface, from the origin, if there is origin, if you draw one normal line, normal up to from O, if you draw a normal to the area of ABC, this is known as H. So that is the mass into body force. So here you are writing it half rho S H. So surface force plus body force is equal to mass. Again, the mass we know into acceleration. Mass into acceleration. Acceleration along x-axis. So along x-axis acceleration, what is that? X. So that is your complete equation along x-axis. Now our consideration is we have to converge this total fluid element into zero. We have to converge the total fluid element into zero. How? That means H tends to zero. Because the stress is such a thing is acting over only a point. State of point. So total fluid element you will compress and make it converges into a point. Because stress is a point phenomenon. So if you reduce the H tends to zero, the total terms will be converged a zero. The total fluid element will comes like a point element. The concept is becomes from here because the stress is always applicable at state of a point. So that's why the H tends to zero. Very finely you get this concept. The stress is a state of a point. That is why the H you have to tends to zero. That means total fluid element converges to zero or converges to origin. In such a situation, what you are getting the equation? So this terms will be neglected. H is zero. This term will be neglected. So remaining part will comes here in the scenario. Tau 1 n be equal to the tau 1 n1 plus tau 2 n2 plus tau 3 n3. So what you are getting here in this equation, first along the x-axis, fraction vector is equal to tau 1 n1, tau 2 n2, tau 3 n2. Similarly, if you calculate the same way, you will get it here that what you are getting it here, tau 1 n1, tau 2 n2, tau 3 n3. And it's along x-axis, it's along z-axis. You see, everything is 2. Second index will be 2. Initially, second index will be 1. And here also the second index will be 3. So 1, 3, 2, 3. Because it's a direction along x-axis, along y-axis, along z-axis. Force balance we are doing it. So force direction. So 3, 3. So this term can be considered as we can write it the summation of tau ji into j. So I is vary from 1 to 3. I is vary from 1 to 3. 1, 2, 3, and J is also varied from 1 to 4. But the concept is here, because J, you see here, J is changing. J 1, 1, 2, 3, 3, 1, 1, 2, 2, 3. This J and this J is with J, and I is the direction of the force. Now here, as the repeating index is there, so from Einstein notation, this summation can be invisible, as there is a repeating index. So repeating index as it is present, we can say there is obviously some summation is there. So no need to put the summation sign. So it is the Einstein index notation. Einstein index notation. So no need of the summation sign. As there is a presence of the repeating index, so obviously there are some summations there. So betterly we could be able to write it in this way: tau ji and j. This is known as the Cochise equation. This is known as the Cochise equation. So, or Cochise theorem. Sorry, it's a not is a just a theorem. It's a Cochise theorem.